The teaching at Vedantu was amazing. One aspect where Vedantu teaching differed from a normal offline coaching was the attention teachers gave to our doubts. No matter how many times we asked a doubt, the teachers would patiently clear the doubt every single time. And they made learning a very fantastic experience for us.
Hello guys, this is Saurav here and welcome to another session on Chemical Kinetics for grade 12. This is lecture 9 and this is the second lecture on Arrhenius equation. This part of the chemical kinetics topic we are discussing, which deals with the dependence of rate on temperature. Okay, so हमने पहले discuss किया है कि in collision theory that if we change the temperature, the number of collisions increases and the rate changes. Okay, rate also increases. So in today's session we would be discussing Arrhenius equation, primarily the mathematical form of what is the temperature dependence. Collision theory हमने खत्म कर लिया है. We have discussed, hello Himanshu, hello Ajay. So we have already discussed collision theory. So we would be discussing Arrhenius equation, and once this gets over, next session में we will be discussing problems. Okay. So let's start today's session. एक बार थोड़ा सा preview कर लेते हैं कि what had been done until now. So we had taken this assumption that to formulate a mathematical relationship between the temperature dependence on the rate of reaction, we would take a bimolecular reaction and would take gaseous reactions. Also, we had identified that all collisions are not gonna lead to a successful collision. All collisions are not successful. A fraction of successful collisions are present. Total number of collisions is 10 raised to 30. Very, very small number of collisions are successful. And what constitutes a successful collision? What constitutes a successful collision is optimum energy and proper orientation. Optimum energy and proper orientation. So if energy and orientation both are pitch perfect, then the reaction would take place. If orientation and energy are pitch perfect, then collision would lead to a perfect reaction. Okay, with that thing in mind, let's move on to what is Arrhenius equation. Arrhenius equation gives us the mathematical relationship between the rate constant and the temperature at which the reaction is being performed. So if we look at this equation, we can see that there is temperature over here and there is rate constant. So the mathematical relationship between the rate constant and temperature is given by the Arrhenius equation. Okay. Now इस equation को हम इस तरह समझ सकते हैं. There is a very simple way to understand this equation. What does this equation and what are the different terms in this equation represent? So I would first tell you ki what are these terms. So K is the rate constant. This is the rate constant. Okay, K is the rate constant. A is pre-exponential factor. Or it is also known as the frequency factor. Okay, okay, pre-exponential factor, or it is also known as the exponential frequency factor. EA is known as the activation energy. This is known as the activation energy, and R is the gas constant. T is temperature in Kelvin. Okay. It's also called Arrhenius. सर मुझे कुछ समझ में नहीं आ रहा है. If you have not watched the previous session, you would not be able to understand. Okay. If you have not watched the previous session, you would not be able to understand. Now, how does the equation come? How does the equation come? Is from experiments that Van 't Hoff had done. Okay, so we are not gonna get into the derivation of this equation. We would start this equation from the idea that okay, we know this equation. Now इस equation का मतलब क्या है? Okay, we need to identify the meaning behind this equation. So what is the meaning behind this equation? Assume that there are 10,000 collisions which are occurring. Okay, assume that there are 10,000 collisions which are occurring at a given second. Okay, within a gaseous system there are 10,000 collisions which are occurring at a given second. Out of those 10,000 collisions, do all 10,000 collisions will have proper orientation? बताइए. Do all 10,000 collisions will have proper orientation? Sir, हिंदी में बोलिए. ऐसा नहीं हो सकता यार. It's not possible. There are a lot of people in the class. Okay, so all 10,000 collisions will not have proper orientation. Out of 10,000 collisions, let's say 1,000 have proper orientation. Out of 10,000, let's say 1,000 have proper orientation. Okay, let's say out of 10,000, 1,000 have proper orientation. Now, will all molecules which have proper orientations, will they have optimum energy? Will all molecules which have proper orientation will have optimum energy? Is that necessary? No. So out of this 1,000 molecules, a certain fraction of molecules have optimum energy. Not necessary. Okay, so I can say that out of this 95% not optimum energy, and 5% have optimum energy. So effectively, how many molecules are eligible, or how many molecules have proper energy as proper orientation and optimum energy? So what is the number of molecules out of 10,000 collisions? What is the number of collisions out of 10,000 which have proper orientation and optimum energy? Only 50. 50 have proper orientation and optimum energy. Okay, only 50 molecules. The equation is exactly what the equation's physical meaning is exactly the same. A represents those molecules or those collisions which have proper orientation. A represents those collisions which have proper orientation, and e to the power minus Ea by RT, isn't that a number? E to the power minus Ea by RT is a fraction of those collisions which have optimum energy. What is the optimum energy? Activation energy. Okay, so if they have activation energy, they can cross the threshold energy barrier. So out of the molecules which have proper orientation, this fraction of molecules have optimum energy. So K represents those molecules which have proper orientation and optimum energy. Okay, so this is the meaning of Arrhenius equation. Arrhenius equation just talks about what is the fraction of molecules out of those molecules which have optimum or proper orientation, which can cross the threshold energy barrier. Is that clear? So So I can say that the physical significance of this relation, is that it's a relationship which gives us the total number of collisions which occur with proper orientation and optimum energy. Okay, this relationship tells us that how many collisions are occurring with proper orientation and optimum energy. Is that clear? Is that understood? So बहुत simple सा equation है, K A e to the power minus Ea by RT. Now, can you tell me at which temperature? So let's say, what are you saying? Okay. So if, let's say there are 1000 collisions which have proper orientation. And this fraction e to the power minus Ea by RT is a number. Okay, e to the power minus Ea by RT is a number, and this number is, let's say, 0.01. So what is the value of K? What is the value of K? We do not have to derive. Okay, we do not have to derive. Don't worry about that. Where does the relation come from? We do not have to derive. Okay, so 10. This means, what does this 10 represents? 10 represents the number of collisions which have proper orientation and optimum energy. Okay. Proper orientation and optimum energy. Now, suppose I want all these molecules which have proper orientation to have optimum energy. Try and understand. If I want K to be equal to A, what is the meaning of K to be equal to A? All molecules which have proper orientation have optimum energy. Okay, if I want this to happen, that in that case E should be equal to 0. Okay, E should be equal to 0. And when would E be equal to 0? When would E be equal to 0? क्या बोल सकते हैं? Or I can say that e to the power minus Ea by RT is equal to 1. When would this be equal to 0? When would this be equal to 0? Think carefully, when would this be equal to 0? So it will be written as 1 by 1 upon e to the power Ea upon RT. Okay, so I can write this thing as 1 by e to the power Ea upon RT when temperature is infinite. When temperature is infinite. Okay, when temperature is infinite, it cannot be equal. क्या बोल रहे हो आप? Think carefully. When K has to become equal to A, what would that mean? This fraction is equal to 1. That means at that temperature, when all collisions becomes equally energetic, okay, K is always less than or equal to A. Yes. So if K has to become equal to A, this value has to become equal to 1, and that will happen only when the temperature is infinitely high. Okay, it is possible only when the temperature is infinitely high. Okay, so if I increase the temperature to an infinitely high level or infinitely high amount, then all collisions will become effective collisions. Okay, so remember that the reaction, any reaction, infinite temperature तो हम achieve नहीं कर सकते, तो any reaction will not be like 100% complete. Some collisions will still remain as the collisions which do not have optimum energy. So with that thing in mind, let's move ahead. If I take the log of that equation, so our equation was like this. Our equation was like this: K e to the power minus Ea upon RT. If I take log on both sides, I would be getting ln k is equal to ln a minus ea by RT. कर सकते हैं आशुतोष शर्मा? या दैट्स करेक्ट. log k is equal to log a minus ea by 2.303 r because ln is log base e. To convert log base e into log base 10, I have to multiply this with 2.303. So this equation would be written as 2.303 log k, which is equal to 2.303 log a minus ea upon RT. So I would get this relationship, and you have to remember this relationship. You will be working with this relationship. इस relationship के ऊपर काफ़ी questions आते हैं, and so you have to remember this relationship. You remember k is equal to a e to the power minus ea by RT. The other relationship that you have to remember is log k is equal to log a minus ea by 2.303 RT. Okay? Now, if I perform a reaction at two different temperatures, if I perform a reaction at two different temperatures, the number of molecules which have optimum proper orientation is not going to change. So log A remains constant, EA remains constant, because I knew because we know from our previous discussion that temperature does not influence orientations. Temperature does not influence activation energy. What does it influence? The number of molecules which achieve activation energy. So when I increase the temperature, let's say there is a different temperature, I will get a different value of rate constant. So there are two different temperatures, T2, for which I am getting a rate constant value of K2. If I take temperature T1, I will get a rate constant value of K1. Now using these two relations, if T2 is more than T1, if I use T2 more than T1, if T2 is more than T1, then K2 will be more than K1. So if I subtract equation 2 from equation 1, I will get the relationship as log K2 upon K1 is equal to EA upon 2.303 R 1 by T1 minus 1 by T2. This is the expression that I would be getting. Okay? What is Arrhenius plot? We'll get to that. There's nothing like Arrhenius plot. There is a plot that I draw between K and log K versus 1 by T. Okay? So this would be the relationship. Log K2 by K1 is EA by 2.303 R 1 by T1 minus 1 by T2. Okay? Is that understood? Chaliye. So this is what has been written over here. Log K2 by K1. If temperature T2 is more than T1, then I would get this relationship. Okay? So, sir, when one rate constant दिया हो तो first वाला use करना चाहिए ना? When one rate constant is given, मतलब one rate constant, I really didn't get you. What are you trying to say? When one rate constant, what is the meaning of your question? Malati, I really didn't get your question. Okay, that when one rate constant is दिया हो तो so previous formula में use करना होता है ना? Yeah, okay. So if there is only one rate constant given, अगर एक ही temperature दिया गया है, then you will use this equation. If two different temperatures are given, then this equation would be used. Okay, it's quite but obvious. If I have just one temperature, I will use just an equation where there is no comparison. Okay. Now let's talk about exothermic and endothermic change. Exothermic change and endothermic change होता क्या है? Exothermic change is one in which heat is given out. Or I can say liberated. And endothermic means heat absorbed. Bond breaking processes are endothermic. Bond formation processes are exothermic. If I take a endothermic and an exothermic reaction and I take these two plots where I am plotting energy versus time, energy versus time, I can get two different outcomes. Exothermic के केस में क्या है कि energy is given out, so reactant, while moving from reactant side to product side, the product has less energy. Okay, while moving from reactant side to product side, the product has less energy. So let's say this is the point where this is the energy of reactant. Let's say this is where reactant is present and this is the energy of reactant, and this is where product is present, and this is energy of product. Okay, this is energy of product. I would have a threshold energy barrier because for all reactions we have a threshold energy. So this is a threshold energy barrier. The plot will look like this. This is threshold energy. This is threshold energy. The extra energy the reactant requires, to cross the threshold energy barrier is activation energy. The extra energy that the reactant requires is activation energy, not the threshold energy. Okay, now this is activation energy in the forward direction. Can I say this? When reactant is converting into product, this is activation energy in the forward direction. Okay, and this would be activation energy in the backward direction. Can I say this? This is activation energy in the forward direction. This is activation energy in the backward direction. Yes, endergonic and exergonic is exergonic is different. Endergonic and exergonic, or exergonic uses delta G instead of this energy delta H. Okay, that uses delta G. यहाँ पे हम delta H use कर रहे हैं because we are talking of exothermic. So when we talk about heat, we are talking about enthalpy, delta H. Exergonic, endergonic talk about delta G. Clear? Now this is the relationship that we would be getting. Now can we say that this difference, can we say that the difference in energy of reactant and product this difference is delta H? इतना जो difference है वो energy बाहर निकल जाएगा. Okay? Yes, Ashutosh, you're absolutely right. So this difference is the energy which will be lost as heat. So can I say, using this relationship, that delta H is energy of product minus energy of reactant? Can I say this? Because it has to be negative, and negative, if we need to get a negative value, for the negative value I need to subtract the larger value from the smaller value. So delta H for this reaction will be E energy of product minus energy of reactant. Okay? Can it also be written as EA of forward minus EA of backward? बताओ, EA of forward minus EA of backward which is a smaller EA of forward, which is larger EA of backward. When I subtract these two, I'll get a negative result. So I would get this. Clear? Is that understood? For ETH, can I say that it is equal to energy of reactant plus EA forward? It can also be energy of product plus EA backward. Yes, the threshold energy is equal to energy of reactant plus the activation energy. Threshold energy is equal to energy of product plus the activation energy in the backward direction. अरे why EA forward is less? Energy of reactant ज़्यादा है ना, तो यहाँ पे ज़्यादा मतलब which needs how much extra energy is needed? You have to cross this barrier. So reactant requires less energy to cross this barrier, or product requires less energy to cross this barrier? Abhinav Singh, when you look at this plot, what do you see? Reactant molecule को ज़्यादा energy चाहिए ऊपर चढ़ने के लिए, और product requires more energy to go in the backward. Reactant requires more energy. Jaideep, reactant requires more energy to cross the activation energy barrier, or product requires more energy to cross the activation energy barrier? So reactant requires less energy to cross the activation energy barrier, so, or threshold energy barrier or activation energy barrier, आप कुछ भी बोलो. Okay, so reactant requires less energy, product requires more energy. That is the reason EA forward is less, EA backward is more. If products require more, तो backward reaction के लिए activation energy ज़्यादा होगा. Okay, it's pretty much evident, very easy to understand. Now if I want to draw it for, अगर मैं endothermic के लिए बनाना चाहता हूँ, okay, if I want to draw it for endothermic, then it means this would be energy of reactant, and here somewhere would be energy of product. Can I say this? Product will have more energy than the reactant. This would be somewhere where the threshold energy barrier would be present, and we would have something like this. We would have something like this. In this case, this is ETH. This will be activation energy in the forward direction. This would be activation energy in the backward direction. Okay, so it is pretty much evident that this difference is delta H. Again, this difference can be calculated. Okay, sir, higher energy means unstable? No, it does not mean that. That's a very flawed conception, that higher energy means unstable. So we would not have had endothermic changes. However, endothermic changes थोड़े कम होते हैं, exothermic ज़्यादा होते हैं, but it does not mean that process is unfavorable. Okay, endothermic does not mean that it's an unfavorable change. Favorable or unfavorable can be identified using delta G, not delta H. Okay, so remember that this will be the result for endothermic, that will be the result for exothermic. Clear? So you could be given questions on this. Now tell me something, is this understood? सभी को समझ में आ गया ये? I hope this is understood to everybody. Sir, is EA always greater than EP in? Always greater? If it is endothermic, then product energy will always be greater than reactant energy. That is the meaning of endothermic. Always का कोई ये नहीं है, means is water always H2O? Sir, is EA always greater than EP? EA always greater, which EA are you talking about? ETH always greater than EP? I'm not actually getting your question. Can you please look at what you want to ask? ETH is the largest energy value that you need to have so as to cross the activation threshold energy barrier. Please check what you want to ask. Okay, is that clear? Now when you use a catalyst, what happens is that in presence of a catalyst, if I would try to draw, in presence of a catalyst for an exothermic change, let's say the change takes place like this. This is without catalyst. And with catalyst, so you get an alternate pathway. So with a catalyst, you get an alternate pathway to convert the reactant into product. Okay, so your threshold energy decreases, so your activation energy for the forward process as well as the backward process decreases to an equal extent. That is the reason the point where equilibrium comes in the reaction will come a little earlier, but equilibrium constant will not change. So a catalyst will only make the reaction come to the state of equilibrium or come to the state of completion a little quicker, but it will not change the concentration. Okay, is that understood? This is what will happen with catalyst. So whenever catalyst is given, activation energy will change, but rate constant will remain the same. Okay. Now, if I want to draw the plot between, K for an Arrhenius equation, if I want to draw the plot between log K and 1 upon T, okay, if I want to draw the plot between log K and 1 upon T, then what would happen is something like this. So this will be log K and this is 1 upon T. Okay, log K and 1 upon T. So log K and 1 upon T, this looks like an equation of a straight line. Y equals to, this is C plus minus M X. So negative slope intercept will be log A and M will be equal to minus 2.3 minus EA upon 2.303 R. In this case, the value of R that you would be using is 8.314 joule per Kelvin per mole, because most of the reactions will have energy units in terms of joules. Okay? Don't use 0.0821 liter atmosphere. You have to use R in terms of joules, because energy generally is given in terms of joules. If it is given in terms of calories, you will use R in terms of calories. Okay? Is that understood? How the graph will look if we use T instead of 1 upon T? If you're plotting it with K versus T, what would it look like? What would it look like? It's very easy to understand. Are you plotting log K versus 1 upon T, or are you plotting log K versus T? Like what is the question? Jaideep, can you like change the equation to have T over here? log k वर्सेस t, मैन log k वर्सेस t आप कैसे प्लॉट करोगे बताओ? यू कैन ओनली प्लॉट इट एज t टू द पावर -1, t के पावर -1 पे ही प्लॉट किया जा सकता है ना. Either you can plot it as 1 upon t or you can plot it as t to the power -1. Graph will always look the same. Okay, if you want to plot it as versus t, you will have to multiply this whole thing with t and you'll not get anything. Will it be a rectangular hyperbola? Man, would you have t, like t यहाँ पे देखो, with the limited amount of mathematics, okay, it will be, I really don't know what you're trying to say, but 1 upon t के respect में हम plot करेंगे. We cannot plot it with respect to versus t. If we plot it with versus t, if this part is already present, let's say a becomes equal to 0, probably we can plot it with respect to t. Okay, इस तरह से आप नहीं plot कर सकते कि आप एक इक्वेशन है वहां पे इस चीज को आपने t बना दिया. You cannot do that. You can't draw it. Okay, you can't draw it. So okay, now there's a very simple relationship that we get. Have you read this relationship? Log of k2 upon k1 is equal to delta h upon 2.303 r 1 upon t1 minus 1 upon t2. Have you read this equation? Have you read this equation? This equation has k. This k is equilibrium constant. This k is equilibrium constant. This k is not rate constant. This is known as Van 't Hoff equation. This is entirely different equation compared to the equation that we have learnt. This k that we have used over here is equilibrium constant, while this is rate constant. दोनों के लिए k alphabet ही use किया जाता है. This is known as Van 't Hoff equation. This part comes in chemical equilibrium in class 11th. The equation looks very similar to Arrhenius equation with delta H replaced by EA. Okay, the only difference is that. Okay, so please do go to your books, look at both the equations. One equation that you are learning in chemical kinetics has activation energy over here, and this has rate constant. In 11th standard केमिकल इक्विलिब्रियम में इसको इक्विलिब्रियम कांस्टेंट और यहाँ पे डेल्टा एच से रिप्रेजेंट करते हैं. ओके, ठीक है. सो विथ दिस आई एंड टुडेज सेशन. नेक्स्ट सेशन विल बी ऑन प्रॉब्लम्स पर्टेनिंग टू दिस इक्वेशन. इस क्वेश्चन पे हम लोग और इन दिस ऑन दिस concept we will take more questions. Next session will be on questions on Arrhenius equation. We might include questions from order of reaction, so please do revise this part and come. Okay, so with this I take leave. I wish all of you guys a wonderful day ahead. ठीक है, चलिए, bye bye.